Welcome students. Today we'll discuss lesson 46. In our previous lesson we have discussed the theory of diffraction at single slit. Now in today's lesson we will discuss the derivation part of diffraction at single slit. Now as the question states, calculate the path difference between the secondary wavelets which starts from the different part of the slits with same phase and reaches the point P on the screen with different phase. Now, as we have already studied, there is a source. This source is producing light in all directions. These lights are made to focus on the slit by your lens L1. Now, your slit acts as your secondary source for your wavelets. So the light coming out of the slits, or let us say the primary wavelets coming out of the slits, gets focused at this point O on the screen. The secondary wavelets coming out of the slits gets focused at the point P on the screen. Now they are being focused with the help of your second convex lens L2. Now note, your secondary wavelets are elevated at an angle theta as compared to your primary wavelets. And note here that the wave coming out of this point A and the wave coming out of this point B, they are not traveling the same distance. So there is an extra path traveled by this point B. And how much is this extra path travel? We can denote it by drawing a perpendicular line at this point. So by drawing a perpendicular line AN on the line BP, we can denote the extra path travel. This is the extra path travel. BN is the extra path travel. So the path difference between the wavelets from A and B will be P equals to BP minus AP, which is BN. The extra path travel will be your BP minus this AP. Now in our case we got the extra path travel is BN. Fine. Now note, this forms a triangle, and in this triangle this angle is also equals to theta. Now if this is a theta and there is a right angle, so I can use my trigonometric properties. So I can say what will be my sine theta? Sine theta is the ratio of the opposite side divided by adjacent side. Your opposite side is BN and your adjacent, or your hypotenuse is, the sine theta is the ratio of the opposite side by hypotenuse. Now in this case my hypotenuse is this one, which is AB. So I can also write my BN as BN equals to AB sine theta. So this extra path difference can be written as AB sine theta. So path difference equals to AB sine theta. Now note, this AB is the slit size or let us say the distance between this point is D. So instead of AB, I can write small d. Therefore, my extra part difference P equals to d sine theta. So this is the expression for part difference in diffraction due to single slit. Coming to our next question. Derive the condition for the dark fringe. Now, as we have studied in our previous class, a dark fringe will be obtained on the screen when there is a part difference of lambda. So whenever there is a part difference of lambda, there will be my first dark fringe. So I can write the condition for the first dark fringe is d sine theta 1 equals to lambda. So this is my first dark fringe, and the condition for this one is d sine theta 1. Now this is my second dark fringe. This is elevated at an angle theta 2, and the part difference in this case will be twice of lambda. The condition for the second dark fringe, d sine theta 2 equals to twice of lambda. Now in the similar manner, we can write the condition for the third dark fringe, for the fourth dark fringe, for the fifth dark fringe, and so on. Therefore, the condition for the nth dark fringe can be written as d sine theta n equals to n lambda, where n is a natural number starting from 1, 2, 3, and so on. So this is the required condition for the dark fringe. Now let us move to the next question. Derive the condition for the secondary maximum. Now, as we have studied, the light coming out of the slit or the primary wavelets coming out of the slits are focused at this point O. So at this point I had my central bright fringe. Fine. Now next, when the extra part difference was 3 lambda by 2, in that case we obtained a bright fringe at this point. So if this is my primary bright fringe, so this will be my secondary bright fringe, or I can say at this point I will obtain my secondary maxima. So the condition for the primary maxima can be written as d sine theta 1 dash equals to 3 by 2 lambda. Similarly, the condition for the second secondary maxima can be written as d sine theta 2 dash equals to 5 by 2 lambda. In similar pattern, I can write the condition for the third secondary maximum, which will be d sine theta 3 dash equals to 7 by 2 lambda. For the fourth dark fringe will be d sine theta 4 theta dash equals to 9 by 2 lambda. Therefore, the condition for the nth dark fringe or the nth secondary maximum will be d sine theta n equals to twice of n plus 1 lambda by 2. You see, this is a odd multiple of lambda by 2, and here n is again a natural number starting from 1. So this is the required condition for your secondary maxima. Moving to our next question and our final question. Draw the variation of the intensity with angle theta in the single slit diffraction. Now, at the center of the screen we had a bright fringe. Now at the center all of the lights were being focused and no light was being lost. So here we will have the maximum intensity. After that, what happened? As we have studied in our previous lesson, the wave coming out of the first part was being cancelled out by the wave coming out of the second part when the path difference, or I can say when the extra part travel was lambda. Fine. So the coordinate will be lambda by d. D is the slit width, the distance or the size of the slit. So at this point I obtain my first minima. After this point, what happens? At this point, what happened? We had divided the slit into three parts, out of which the two parts cancel each other. The third part only contributed to the bright fringe, or let us say to the secondary maxima. Therefore, we had our maxima at this point, but it is only due to the third part of the slit. Therefore, we had a bright fringe but with a smaller intensity. So in this case the intensity also decreases. Now as we go further, again we will get minima, then again we will get a maxima but this time lesser intensity, again we will get a fringe, again there will be a maxima but lesser intensity, and this will continue so on till the dark fringe or till all of the screen becomes dark. So this is the variation of the intensity. Same will be applied on the other side of the graph. Fine. So this is the variation of the intensity with angle theta in a single slit diffraction. Fine. So that's it for today's class. And if you have any confusion, you can ask. I will re-explain it to you again. So thank you.